Welcome to this video lecture. My name is Mark Scythian. The date today is February 24th, 2021. The title of this lecture is DC Electrical Circuit Analysis, Circuit Voltage Load and Total Resistance. So here we have a DC complex series parallel circuit in an automotive application pertinent to an HVAC system, its temperature sensor, blower fan, and a lighting system. So we know that direct current involves electron flow from positive to negative. So after the automobile is started and the engine's running, the selector switch springs back to the on position. So here we have a potential current available of 760 amps flowing on series without any resistor voltage drops on series, meeting a parallel circuit junction to power the HVAC system with 0.24 ohms on parallel resistor circuit. So if we apply Ohm's law, 12 volts divided into 0.24 ohms will draw 50 amps of current. So now we're left with 710 amps potential current availability, which then meets a parallel 2 resistor cluster on series with a combined resistance using the product sum rule of 0.0043 ohms, which then multiplied times 710 amps will cause a 3 volt drop, allowing 9 volts to flow to the second parallel circuit, which is always energized once the switch is at the on position. A combined resistor, a combined 2 resistor total resistance for R4, R5 is calculated, again using the product sum rule of 0.45 ohms. So therefore 9 volts divided into 0.45 ohms will draw 20 amps of current to the temperature sensor. We know that voltage remains constant on parallel circuits, whereas current remains constant on series circuits. When resistors are on series, voltage drop will occur, whereas the current draw will occur when resistors are on parallel. So now we have 690 amps flowing to the third parallel circuit, which does have an on-off switch, just like the HVAC system. R6 and R7 on parallel have a combined total resistance of 0.15 ohms using the product sum rule. So when 9 volts is divided into 0.15 ohms, 60 amps of current will be drawn to power the blower fan. This then leaves us with 630 amps of current, also at 9 volts, which then flows to the last parallel circuit, the light bulb or the lighting system, which will draw 10 amps of current based on 9 volts divided into 0.9 ohms on R8. We must then add a follower circuit so that R8 remains on parallel, allowing for 620 amps of potential current to flow back to the ground, in this case the battery's negative terminal. This design was customized based on an upgrade of different power requirements for an aftermarket HVAC temp sensor and blower fan installation or upgrade based on the redesign of the required resistances involved. And so therefore the heat rating based on a much larger gauge wire will require a 10 ohm resistor. Since this is a digital circuit on a late model vehicle, these resistors are programmable and or through PLCs. However, on older vehicles, more than 20 to 30 years in the past, they more than likely would be digital or hybrid digital analog circuits or pure analog circuits, which then require the desoldering of resistor circuits on external bus modules and or unit relay configurations, which can be accessed through the specifications in the repair manual as well. So therefore, when selecting combination resistors, especially two resistor clusters, we can then restate the product sum rule and allow the second resistor to take the place of X so that the required specialty resistance can be calculated by solving for X algebraically. We do know about the product sum rule for calculating two resistors in parallel. When combining three resistors in parallel for total resistance, we can use the inverse sum fractional rule listed here. And then combining resistors in series is simply the additive rule. We simply add the resistors together, their values. So Ohm's law, of course, is E is equal to IR, which is basically saying that 1 volt will equal 1 amp pushing 1 ohm of resistance, and where applicable on series circuits is when calculating voltage drop, and on parallel circuits when calculating current draw. And of course we went over the difference between series and parallel electrical circuits. Series circuits have constant current, whereas parallel circuits have constant voltage. So to get the total resistance of the entire circuit, we would then draw a resistor diagram with the original resistor configurations stated, uncombined, and then we would then, in this case, select the R4, R5 combination, which we have 0.45, R6, R7, 0.15 ohms, and then R8 is by itself, which is 0.9 ohms. So we simply combine these three parallel resistors, including the combined resistances. We can do so here with A, where we use the inverse fractional sum rule. We calculate 0.1 ohms total resistance, which we redrew the circuit afterwards as such here in 1 of 3. Then we follow. Then after that, we can quickly combine R2, R3 with R4 to R8, which is just adding these together in series. So when we do so, we get 0.1043 ohms. Then redrawn for the second redraw circuit, we have R2 to R8 combined with R1, and that's just a simple product sum resistance combination of two resistors, which we have here in B, which actually totals, sorry, C actually, we did the sum here for B, actually we went ahead, and then C is simply the product sum rule for combining these two resistors in B, and it's 1043 times 0.24 divided into 0.1043 plus 0.24. So that's the golden magic value for doing a lot of accurate analysis in DC circuits, is to find the total combined resistance of all resistors in both parallel and series, 0.0727 ohms. So now we have quite a lot of controllability on the circuit's metrics with or without actual instrumentation, for which we calculated quite relatively quickly. So Total resistance 0.0727 ohms, with a current draw 50 amps at the HVAC system, 20 amps at its temperature sensor, 60 amps at the blower fan, 10 amps at the light bulb or lighting system. A total of 140 amps are needed. We have a source voltage of 12 volts. Theoretical power draw would be the 50 amps times 12 volts, 600 watts, plus 20 amps times 9 volts, 180 watts, plus 60 amps times 9 volts, 540 watts, plus 10 amps times 9 volts, 90 watts. So we have 1410 watts theoretical power draw. Now the actual power draw should be very close to the theoretical power draw. The actual power draw gives us the upper hand for overcoming close tolerance circuit specifications. So P is equal to IV is equal to power. So we have 140 amps times a circuit voltage draw of 10.18 volts. How we got that is if we step back one, we have the circuit voltage load, which we need to calculate first, which is the actual circuit load drawn from the battery within the circuit, but not the actual theoretical or source voltage 12 volts. So E is equal to IR. We know we have a current draw of 140 amps, and we know that the total resistance of the entire circuit, all resistors both series and parallel, equals 0.0727 ohms. So when we multiply these two out, we calculate an actual circuit voltage load of 10.18 volts DC, or about 10.2 volts DC drawn out of the battery. So when we multiply 10.18 volts times 140 amps, we calculate 1425.2 watts actual power draw, which is very close to the theoretical power draw. So this metric here, the actual power draw and the circuit voltage as well as the total resistance, will allow for very close tolerance and accurate circuit metrics when doing any customization, upgrades, modifications, and redesign. So our proof here is actual power draw 1425.2 watts divided into circuit voltage load 10.18 volts DC will equal the current draw involved, 140 amps. So if we check it, 1,425.2 watts divided into 10.18 volts DC equals 140 amps. So that is correct. You may want to study the design here and realize that the actual circuit voltage load is somewhat less than the source voltage, in this case 12 volts, because then by isolating the circuit voltage load, you then have the ability to make very close tolerance, highly accurate calculations which are consistent with circuit specifications and limitations. Thank you for watching this video and have a great day.